still related to duality, we are going to talk about something that is called complementary slackness. So here's the theorem. Suppose we have a feasible primal solution x and we have a feasible dual solution y. So the first key is it must be feasible in primal and y must be feasible in dual. Then x is primal optimal and y is dual optimal if and only if. So the second key is that if we want to ensure that both x, y are optimals, then this must happen. So this is called complementary slackness. So Si, the slack from the primal variable, times Yi, the corresponding dual variable, the multiplication of them must equal 0. Similarly, the excess variable from the dual problem times the corresponding variable in the primal problem, the multiplication must be 0. So this is called complementary because the complementary problem of primal is the dual and the complementary of the dual is the primal. So just to spell out that result, so it says that SIYI equals 0. It means the ith slack variable in the primal problem, if it is greater than or equal to 0, it implies the ith dual variable equals 0. Similarly, if the ith dual variable greater than or equals to 0, so this is yi, it implies that the ith primal slack variable equals 0. And then for ej times xj, we can say that if the jth dual excess variable greater than or equals to 0, it implies the jth primal variable equals 0. And similarly, if the jth primal variable greater than 0, it implies that the jth dual excess equals 0. We may also interpret this result like this. If a constraint is non-binding, so it has either slack and excess which is non-zero, so that's why it is non-binding, then the corresponding variable in the complementary problem equals 0. So this is also how we may interpret the complementary slackness. Well, to convince ourselves that in the optimal solution, both for the primal and the dual, complementary slackness must happen, let's look at the Dakota example. So the one on the top is the primal problem and the one in the bottom is the dual problem. So let's check if this happens. So S1 equals 24, Y1 equals 0. So S1 times Y1 equals 0 indeed. S2 is 0, Y2 is 10, so again 10 times 0 is 0, and then S3 equals 0, Y3 equals 10, so the multiplication is again 0. E1 times X1, E1 equals 0, X1 equals 2, so the multiplication is 0. E2 equals 5, X2 equals 0, so the multiplication is again 0. And finally, E3 times X3, the multiplication is also 0. So indeed, at the optimal condition for both primal and dual, complementary slackness happens. And then we may also see complementary slackness from the point of view of shadow price. I think we have talked about this before. So let's say we are looking at S1 times Y1 equals 0. S1 corresponds to the slack in the lumber constraint. So we have slack equals 24. It means that we do not consume all the lumber that we have. We only consume 24, so we have slack 24 lumber. So because we still have the slack of lumber, then the shadow price for lumber equals 0. Right? Remember that dual solution is the shadow price for the corresponding constraint here. So because we still have extra lumber that we do not use anyway, so the value of an extra lumber equals 0. We do not need any more lumber. So complementary slackness also shows that if we still have the slack for a resource, then the corresponding dual variable or the shadow price for that resource equals 0. Now what about S2, Y2? So Y2 equals 10, which means that we know for the second type of resource, which is finishing constraint, an additional unit of finishing hour has the value, because currently we consume all the finishing hours that we have. So again, it shows that if the shadow price is not 0, it must be that we have consumed everything we have for that resource in the current optimal solution. So again, that's why the multiplication becomes 0. Now what about E2 times X2? So we know E2 equals 5, such that X2 equals 0. X2 equals 0 means that we do not produce table. And if you remember this calculation here using the shadow price, the reason that we do not produce table is because the total resources that we use to produce table worth $35, while the selling price of one table is only $30. So that is why we have excess of 5. The amount of resources that we use equals 35, but the selling price only 30. So there is an excess of $5. So that's why, because there is an excess, the value of the resource is larger than the selling price. That's why in the primal problem, we do not produce table. So we have seen how complementary slackness may also explain the relationship between whether we have slack or excess and the value of the complementary variable. Now we are going to see that complementary slackness may also help us solving the complementary problem, which means that if we are given the primal LP and the optimal primal LP solution, we may use complementary slackness to obtain the dual solution. Okay, let's do this with Dakota problem. So given the primal LP for Dakota and the optimal solution for the primal Dakota problem, we're going to solve the dual problem. Okay, so this is the dual problem for Dakota, and then we're going to use complementary slackness. So first, we may notice that S1 equals 24. Because S1 times Y1 must be 0, then it must be the case that Y1 equals 0, right? Because this is non-zero, then Y1 must be 0. And then we know X1 equals 2, so it must be that E1 equals 0. E1 equals 0 means that this desk constraint is a binding constraint at the optimal solution. Binding means that this sign becomes equality at the optimal solution. And then X3 equals 8, which means E3 equals 0. Again, because E3 times X3 must be 0, because X3 is positive, then E3 must be 0. This means that the chair constraint is also binding at the optimal solution. Okay, so now we have enough information to solve the problem. Y1 equals 0, so we may just ignore Y1. And then we have the first constraint becomes equality, the third constraint becomes equality. So the first constraint becomes 4y2 plus 2y3, 4y2 plus 2y3 equals 60. The third constraint becomes 1.5y2 plus 0.5y3 equals 30. We have two constraints, two equalities, we have two equalities, two variables, so we may solve y2 and y3. y2 equals 10, y3 equals 10. Such that now we may complete our solution by calculating that E2 equals 5. So we've seen how we may use complementary slackness to show the relationship between resource and the shadow price. We have also seen that we may solve the complementary problem using complementary slackness. Now here's a question. Given the primal problem and the primal optimal solution, since x2 equals 0, using complementary slackness theorem, we know that E2 in the dual problem must have a non-zero value. Is this statement true or false? I will give you a pause on the video to give you the time to think about it, and I will return with the answer after the pause. The answer is false. So if x2 equals 0, according to complementary slackness, E2 may be 0, may be non-zero, right? So you can't say for sure in this case. What you can say for sure is if it's the other way. For example, x3 equals 8, 8 is definitely non-zero, then you can say for sure that E3 must be 0, such that the multiplication becomes 0. Okay, so that's the end of this video, and then in the next one we're going to go back and look at simplex algorithm again, but now we're going to talk about dual simplex. So see you on the next one. Thank you.